In this segment, we'll look at the relationship between area and definite integrals. So basically, what we've done so far is we've talked about indefinite integrals of this form, and we talked about how they were connected to antiderivatives and derivatives, and what all that had to do with each other. But now what we're going to look at is a related notation, and why they're related we'll talk about a little bit more later. But for now, we'll just sort of treat them as separate things. So we'll have some notation like this. Okay, so what this is the integral of f of x from a to b, whereas over here there's no a to b, so this is indefinite. And this one is definite. Okay, and there is a very deep connection between these, and we'll talk about that after a couple of sections. But what I want to explain, at least in this video, is sort of what this is supposed to represent. So previously, before, we talked about how the indefinite integral is basically just representing antiderivatives, and so we've covered that. So what is this symbol supposed to represent, and how is that different from this thing over here? Well, in the last section we talked a lot about area, area contained by some sort of geometric figure, or in the sort of calculus context, area underneath a curve, so between the curve and the x-axis. And so that's what this symbol is going to actually represent. So the definite integral, this represents net area under a curve. Okay, now what do I mean by net area? If you've, say, ever studied economics, you know the difference between net and gross. So gross revenue is how much money you actually have coming in, and your net revenue is however much money coming in minus whatever your expenses are. So there might be some notion of a negative quantity here. Now, I don't actually mean that the area can be negative, but we're going to think of certain areas as counting as negative. So let me draw sort of a picture to illustrate when area can count negative. So if I've got some coordinate axes there, and then I'm going to draw a curve here in brown, and so that'll be something like, oh, I don't know, just something like this and that. Then if I'm going to consider this curve, and let's say that this point over here is A, and that this point over here, let's scoot this out, is B, then the area between the curve and the x-axis can be sort of divided into two pieces. There's the stuff over here, which I'll put in blue, and then there's also the stuff over here, which I'll shade in red. And so the net part here refers to the idea that the red stuff counts as negative. Okay, and the reason we're going to think about it as counting as negative is because the area that's enclosed by the curve and the x-axis, that area is actually below the axis. So anything below will count as negative. Anything above, like the blue stuff, will count as positive. So the blue area counts as a positive. Okay, and so the net area would be the positive stuff taking away the negative stuff. So we'd have blue minus red, and the minus is capturing the counts negative part. Okay, so in this sort of sketch, there's a little bit more blue area than there is red area, so we should expect that for this particular curve, the net area is some sort of positive number, but you could easily imagine a situation where the net area was negative or even 0. So for example, if the red stuff and the blue stuff exactly are the same, then when you do the subtraction, they would cancel each other out, and so there would be no net area, even though there clearly is area in a geometric sense. Okay, and so this idea here is what we mean when we say this symbol. Okay, so we've got a function. In this case, the function is the curve that I've drawn in brown, and the a and the b are whatever the x coordinates of these 2 points that I'm interested in. Now, in my example here, they were roots of this function. They don't have to be roots, but in many cases they are. Okay, so the definite integral represents the area, the net area between a curve and the x-axis, and it's sort of stopped on the left and the right by some specific numbers a and b. So in this case, we get this notation. Okay, so in the next segment, we'll look at a little bit more specific example of one of these where the function actually is some sort of algebraic formula and a and b are specific numbers. Okay, so in this example, we'll take a more concrete function, and we're going to look at the function f of x equals, say, 1 minus x, and we'll let x be between, say, 1 and 3, just as an example. Okay, so first off, let's just sketch this situation and kind of see what this area looks like. So actually, I'll do it with a nice straight line so it's clean. We'll get, say, a nice little set of coordinate axes here, and then I'm going to mark off 1, 2, and 3. And then let me just graph this line real quick. So 1 minus x, the intercept will be here. It'll also go through this point here. And so like in the last segment, I'll do this in brown. So we've got a straight line, and so the graph would be something like this. Okay, and 1 and 3 is here and here. Oops. So we've got 1 and 3, and then I want to shade in the area that is between this curve and the x-axis. And I'll go ahead and do that in red here because, as we can see, it's all below the x-axis. So all of this stuff here is the area between this curve and the x-axis where x is allowed to run from anywhere from 1 to 3. Now if I change this 1 to 3, then I change the shaded area. So for example, let's say if I changed the x's to be between 0 and 1, then I would get this stuff over here. So changing the available values of x will change the sort of shaded region, the area that we're looking for. Okay, so let's write down an integral to represent the red area. Okay, so this stuff here will be, well, it's going to be an integral from something to something. The function is this guy. And you don't have to put parentheses there when you write it, but it's a good idea on the computer to go ahead and do it because the computer sometimes gets confused as to whether or not you mean x dx or the whole thing dx. Now, in one of the Webassign exercises, they actually have the dx there already for you, so you don't have to type that part. You just have to type whatever goes here, and it's up to you to figure out what that is. I'd go ahead and put the whole thing in parentheses, and that'll just save you some headache. Okay, anyway, for the red area, what are the ranges of the x values? Well, the red stuff was from 1 to 3, and so my lower bound is 1, and my upper bound is 3. And you can think about that as to where the area starts and where it stops, and then this part tells us how far the area goes up or down for any given x value. Okay, so the red area is this one. And so actually let me circle that in red. And let's do the same thing. Let's write the area for, or the integral for the blue area. That would be the integral from 0 to 1. Oops, not f of x. We have a specific function here. So here our function is still 1 minus x. So this integral would give me the blue one, the blue area, and this integral goes with the red area. Okay, so not too bad. Now here we started with a function and some sort of description, and we did the graph in order to figure out what the integral was. We could have started from a graph in the first place, and this is what your exercise will actually look like on Webassign. So you know, if I had given you a graph and sort of shaded in an area, could you figure out what the bounds are and the thing you integrate? The thing you integrate is pretty easy. It's just whatever the formula is that describes the curve, and then the bounds are wherever your area starts and stops. So let me just sort of sketch one more example here. Let's say that I had something like, let's see, -2 here, 2 here, and I'll go up 4 here, and then the curve I'm going to draw is supposed to be a parabola, but we'll see if my art skills can do it. Okay, so I've got a somewhat pathetic parabola. So let's say that the area that that was given was the green stuff, and I'll shade in that area here in a second. And let's say that that's all of this. Then, oh, and I need to specify what this parabola is. It's the graph of y equals 4 minus x squared. Then the green stuff will have this as its area, net area. It'll be -1 to 3, because I started at -1 and I ended at 3, and then the function is 4 minus x squared, and then I need a dx. So this integral represents the area of the green stuff. Okay, so your Webassign exercise will look kind of like this, and the pieces that you've got to figure out for it are two things. One, what is the function that you need to integrate? So what function is involved, and so you'll figure that out. And then the other thing you've got to figure out is what are your bounds here. So, but all of these you can get based on a graph, again, the information you've given that's given to you. So just kind of think about it like we have here, and it should be pretty straightforward. Now, one thing I wanted to just kind of mention before we quit is that in the case of, say, this blue or this red area, it should be pretty obvious what the actual area is, because both the blue and the red area are triangular. Okay, so in situations like this where the figures or the areas are obvious geometric things that you know from elementary school, you can compute these areas very, very quickly just by using a geometric formula. And when I show you guys in class how we compute this the long way, then sure enough, we will get exactly what geometry tells us we should. That comes to a screeching halt, though, when we have a figure which isn't necessarily something that's an obvious geometric formula. So for example here, this parabolic stuff, there's not necessarily any formula that you learned in elementary school for what this area is, and if I drew some random squiggle, then the odds of there being some obvious formula that you learned in school goes way down. Now, as it turns out with the parabola, there is kind of a cute way that you can do it using some stuff that Archimedes discovered, but that's a little special. Most of the time, though, you can't do this with obvious geometry, and fortunately, there'll be some shortcut ways for how you can compute this. But we'll talk about the details as to how you do this the long way in class, and then in a later section, we'll talk about what the shortcuts are.